So, hello students, today we are going to see what is the size of the nucleus. So, in atomic and molecular physics, we always deal with the distances which are in angstroms, and we know that 1 angstrom is equal to 10 raised to minus 10 meters. But when we deal with the nuclear physics, we deal with the distances in femtometers. Now, 1 femtometer is a 10 raised to minus 15 meter. I have written here, so 1 femtometer is a 10 raised to minus 15 meter. So the range of the nucleus or the nuclear size in the range of the femtometers. Now we know that this nucleus is not a classical mechanical entity. As I always say, the nucleus cannot be considered as a hard ball, as if it is having some sharp boundaries. Okay, so nucleus consists of protons and neutrons, but the distance up to which the protons and neutrons are there, and after that protons and neutrons are not there, such a sharp boundary is not present for the nucleus. Okay, so we can say that the classical mechanics cannot be applied to the nucleus. So let me show you the graph of the charge density versus the distance. Okay, so we know that this nucleus consists of protons and neutrons. So these are the charges which are present inside the nucleus, and suppose this is a nucleus and these are the number of the nucleons which are present inside the nucleus, and as I have said that it is not having any sharp boundary. Okay, so this is a quantum mechanical picture of the nucleus. Now if I take the distance from this center, and if I draw the graph of the charges which are distributed along with the distance, so it has been seen that the charge distribution remains constant up to certain distance, and then it goes on decreasing exponentially. So this is R, and this is the charge distribution. So I can say this is the number of protons or number of neutrons collectively. Okay, so here we can see that when this distance R is equal to 0, means at the center. Okay, and as the R goes on increasing, it means that when we move away from this center, so the charge density remains constant up to some distance, say let's say up to here, and after that this charge density goes on decreasing exponentially. So we can say that there is not a sharp boundary is there. So the nucleus is not like a hard ball. Up to some distance nucleons are there, and after that nucleons are absent. This is not the case. This is not the picture of the nucleus. Rather we can say that the charge density means the number of protons and neutrons, they are uniformly distributed up to some distance, and after that probability of finding the protons and neutrons goes on reducing exponentially. Okay, so this is how this nucleus looks like. Okay, now as I'm telling you that the nucleus is not having any sharp boundary. Okay, so we cannot say the nuclear radius. See, when it is not having any sharp boundary, you cannot speak about the nuclear radius. Rather, you can use the proper word which is called as a nuclear extent. Let me write it here. So, let me write it as R. So, this R is given by R naught a raised to 1 by 3. See here. So, nuclear extent or the radial extent of the nucleus, it is given by the formula R is equal to R naught a raised to 1 by 3, where this R naught is called as a shell cap, and its value is 1.2 femtometers. And but obvious, this A is nothing but the mass number. So see here, as this value R naught 1 that remains constant as 1.2 femtometer, when we go from the lightweight nuclei to the middleweight nuclei to the heavier weight nuclei, the inner core that goes on increasing with the increase in mass number, but this is shell cap, so this distance, so this shell cap remains constant. For example, the picture will be clear if we take few examples. See 14, and if you have taken any middleweight nuclei like Fe26 56. And if we have taken another example of a heavier weight nucleus, say uranium 92 238. Okay, so by using this radial extent formula, we can evaluate the radial extent of all these nuclei. So if you take if you use this formula for these three different elements in a periodic table, we can get, so this R is equal to R naught, which is 1.2, and A mass number, which is 14 raised to 1 by 3. We can use the same formula and 56 raised to 1 by 3 and then 238 raised to 1 by 3. It was found that this nuclear radial extent was found in a range of 2 to 8 femtometers nearly. Okay, so the nuclei which are lightweight, middleweight or a heavier weight, so the all the elements or all the nuclei which are present in a periodic table, they will fall under this range nearly. So the nuclear radial or the radial extent of all the nuclei in a periodic table, starting from the lightweight, middleweight to the heavyweight nuclei, will fall in a range of nearly 2 to 8 femtometers. You can take this as an exercise and you can evaluate the radial extent of the nucleus of these three elements. Okay, now see here what happens is, we know that now this nuclear range is in the 2 to 8 femtometers, and we know that this radial extent is going to increase with the increase in mass number. Okay, now suppose, so this is the nucleus, we are speaking about the nucleus and not the atom. Now suppose this is the nucleus of the carbon. Okay, it will consist of 14 nucleons. Okay, suppose these are the 14 nucleons. So as I have already said, so this R naught is a shell cap which remains constant. So this R naught, that remains constant for all the nuclei, and what goes on increasing with mass number is the inner core of the nucleus. Okay, so when I take this Fe, let me show this shell cap with some different color. So when this shell cap starts, let me show it with some yellow color. So this shell cap remains constant, but the inner core will increase. Now as this is a Fe nucleus, it will have more number of nucleons, so the inner core will be bigger one, but the outer shell, which has been drawn over here, that will remain constant. Same will be the case for the uranium 90 to 238. So the inner core will be bigger, but this outer shell, so this will remain constant. So by using this formula, R is equal to R naught I raised to 1 by 3, we can evaluate the nuclear radial extent